All right, so let's talk about this pendulum. I have an example here. I've got a 2 kilogram pendulum is released and swings down 5 meters. This is a big pendulum. It's kind of unrealistically big, but we're going to go with it. How fast is the pendulum moving at the bottom of its arc? So I want to show you how we can use energy to figure out how this GPE turns into kinetic energy. I'm going to be doing a bunch of math here. Don't worry if you feel like you couldn't produce this on your own. We're going to build up to it over the course of a unit. All right, I'm going to draw a little picture here. So I've got this pendulum. It's going to be released from rest. It's going to swing down. And this height difference is 5 meters. All right, I'm going to organize my work using something called an energy bar chart. We're going to learn more about this later. And the reason why I have 2 of them is we're going to look at sort of at the beginning or initially when the height of the pendulum is at 5 meters, and then we're going to look at the end when the height of it is 0. Obviously, the pendulum's going to swing back up and go back and forth, but we're just looking at it, the 2 points you looked at in your lab. And we're going to be looking at 2 kinds of energy that this pendulum has. It has kinetic energy sometimes, and it has GPE sometimes, and sometimes it has both. So initially at the beginning, it's not moving. You haven't let go of it. And it just has GPE. And I'm going to draw a little bar to show that it has energy stored as GPE. When it swings down to the bottom, it loses all of that GPE, and all of that GPE turns into kinetic energy. Remember, energy can be neither created nor destroyed. It just gets transformed from one form of energy to another. Now we're going to do some calculations. I know that the equation for GPE is mgh. I'm going to plug in what I know. The mass is 2. I'm going to use 10 for G to keep it simple, and the height is 5. And I get 100. And the unit for energy is joules. I'm going to write 100 joules on top of this bar chart just to show that that's how much energy we have. So what that means is that this energy is all going to get transformed to kinetic energy at the bottom, and we're going to have 100 joules of kinetic energy at the bottom. I'm going to set up an equation, and I'm going to see what I can figure out now that I know that I have 100 joules of kinetic energy. I'm going to plug in 2 for my mass, and it turns out I can solve for V. So I'm going to do that. So I get 100, these 2's cancel out, equals V squared. Oh, nice. V equals 10 meters per second. All right. So here's how we're going to be using energy eventually in the future to solve some problems. I want to show you something else, though, that's kind of interesting. This pendulum, it dropped 5 meters by swinging along this arc. But let's see, what would the velocity be if that mass were just dropped straight down? Would we get a different velocity? All right, so that brings us to example 2. We have a 2-kilogram ball, same mass, and it's dropped a height of 5 meters. How fast is the ball going right before it hits the ground? Well, you can use kinematics for this. And you can use energy. Let's use kinematics. So I'm going to set up my Vtax. My V initial is 0. My V final, that's what I'm trying to look for. I don't know the time. I know my acceleration is -10. And I know my delta x. I got to put in -5 because it's going down. Let me put in some units here. So I want to find V final. So the equation I'm going to use is V final squared equals V initial squared plus 2a delta x. I'm going to plug in the stuff that I know. This is 0, 2, -10, -5. That goes away, and this becomes 100, and my V final ends up being 10 meters per second. Look at that, that's amazing. We get the same exact velocity for the pendulum swinging down 5 meters as we do for a ball being dropped straight down 5 meters. This is going to become important later on.